Hello to everyone. This is Paolo Zanardi. I'm a professor of quantum physics at the University of Southern California in Los Angeles. And I'm here today trying to explain you in a very simple fashion what the Heisenberg uncertainty relations are all about. And in order to do that, I will play a little game with you. So I'm a thought experiment. Let's suppose you are given a bunch of pebbles and they come in two different shapes. They're either square or round, and they come in two different colors as well. They are either white or black. And now we want to determine whether, which of the two properties. Well, we have four possibilities right now altogether. And we have a whole bunch of those, and we fill a box with all those pebbles of different shapes and colors. And then we reach the box and we draw one of those pebbles out. And let's say we first measure the shape of that, say with our hands and eyes closed, in such a way that you can learn what the shape is, whether it's a square or it's a round, but you will not learn about the color, whether it is white or black. And let's say that while you perform this, after you perform this experiment, you drop all the square pebbles on a new little box on the left, and if they are round, you toss them on a little box on the right. Okay, now when you're done that, you have performed, you reach the box many times, and now you have a whole bunch of square pebbles on the right and a whole bunch of pebbles on the left with different shapes. Let's say that we focus on the box on the left where they are all supposedly square. And now we're going to check the color of this, but in some funny way that doesn't allow us to see the shape anymore. And by the way, it shouldn't matter, right? Because we already know what the shape is. But let's say we're just allowed, with a tiny aperture, like tiny holes, to see the center of the pebble, and we can learn what is the color, but still we are, we don't know what the shape is, okay? So now let's say we pick the squarest one and we measure in that way the color, and again we end up having two boxes, say on the left the white and on the right those that are black. And now you say, okay, if I pick one of these two last boxes, I know that what is in there is certainly a square pebble with the white color, say, or a square pebble with the black color. And then just to double check that, so now you should know what I mean. You should know in principle you have fully determined both at the same time, shape and color. But what happens now that if you take these pebbles from the left box, those that are now assumed, or you thought they were, square and white, and then again you check the shape of this, namely you reach this box, and with your hands you just double check that, of course, they should square like they were supposed to be, and it turns out they're not. Half of them, they are squares, but the other half turns out they are rounds. So the fact that you have learned the color made the shape completely uncertain. And you can play this game the other way around, like in the first stage of the process, you measure, as we say, the color, and you split the two subsets according to the result of that measurement, and then you perform a shape measurement with your hands. And now if you were to perform again one color measurement, you would find, to your great surprise and maybe horror, that again, once you have learned the color, then the shape is completely undetermined. So this is a sort of a trade-off that in quantum theory goes well beyond, of course, the example of the color and the shape. For example, the position of a particle and the speed of a particle. If you know one, then it turns out you don't know the other so much, or there's a trade-off, right? The more you know about the one, the less you know about the other. For example, let me conclude this in 1 minute. If a particle around and you want to determine the position, the particle is like a little bullet going, around in space, forming a trajectory. So in order to determine at a given time what the position is, we have to see the particle there in this given point in space. And in order to do that, the way we do that is with our eyes, we collect the light that has been scattered, that has been reflected by that particle. Of course, if you want to be very precise about the location, we have some, uncertainty there, but you need a very short wavelength light. This is a little technical, but the point is that, if the wavelength is very short, and this is exactly what you need in order to make very precise your measurement of the location of the particle at a given time, then it turns out that this light is very energetic because light is made out of photons, little particles of light, whose energy, it turns out, is inversely proportional to the wavelength. But now if you are shining these photons, short wavelengths, namely high energy, these are sort of kicking the particle around. So you will learn with greater precision what the location of the particle is. But since now the particle has absorbed in this bouncing process with the photons, has absorbed some of the energy of the photon, namely now the velocity of the particle is completely undetermined, or there's some uncertainty on the particle velocity that is related to how precise you try to locate the particle in space. And you could actually argue that this is the same. The more precise is your momentum or your velocity measurement, then the less you know about the location of the particle. But now here things that will start to be a little technical, and I guess I will just stop it here. Hopefully you enjoyed that. Thanks a lot, guys, and until the next time.